Hi, for the lecture today we are going to talk about finding maximum and minimum points. Let me write the title here, finding maximum and minimum points of a function. To motivate the topic, let me give you this example. Suppose you want to install a solar panel to catch the sun rays and convert it to energy and put it to some good use. The question immediately arises, at what angle should you install your solar panel to catch the most energy for a given day? When you are studying these kind of problems, you typically take a variable like your angle of installation and develop a function. Such a function might look something like this. To simplify the issue, maybe you have a function perhaps look like this. So on this side you have the angle, and here you are recording the energy you are capturing. At some angles perhaps you're not catching much energy, some other extreme angles also not good. There is some intermediate angles at which you have the best output. You want to find that point. Well, we have a name for this type of a point. We call this a maximum point. So this is the max. We say the maximum value occurs at this point, and the value is this height. The height of the function at that point is the maximum value. The point at which it happens, the x of it is the x of this point. And the objective of this section is to use calculus to get us to this issue. In general, you might have some function that has several maximum and minimums. We are going to have some terminology for this situation. This point, as you see on the picture, that looks taller than the neighboring points, is referred to as a relative maximum. Relative maximum, so this point is taller than its neighbors. Perhaps this point is taller, or perhaps somewhere else this function might become even taller than this one. So relative simply means relative to the neighbors. Sometimes instead of using the word relative, they use the word local. So local max is another word for the same thing. Similarly, we have local minimum. So this is point which is called the local min. It is lower than its neighbors. To be sure, there are other points of the graph that are lower than this, meaning they have a smaller y values, but compared to the neighbors, this is the lowest point. Another word for this would be a relative minimum. As you see that this graph has several local max. Here's a local max, here's a local max, here's another local max, and has several local mins also. So these are local minimums. Suppose, for the sake of argument, that this function just settles down and so among all these local maximum we have found, there is one that perhaps stands the tallest. That one we are going to refer to it as the absolute maximum. So here is absolute max. So absolute max is a local maximum that also beats all the other local maximum. So it is truly the tallest point on the whole picture. Sometimes instead of using the word absolute, they use the word global. Global is opposite to local. Similarly, you have the concept of a global minimum or absolute minimum. So in this picture, perhaps it's not drawn clearly enough to see where the local minimum is. Perhaps it doesn't have a local minimum. We are going to go ahead and develop procedures for finding these. One of the items that is going to be very helpful for us is the so-called Extreme Value Theorem. The word extreme is a word that used to indicate either maximum or minimum. So extreme is inclusive of both maximum and minimum. Either of them is covered by this. This theorem says the following. It says if you have a function that is continuous, let's go ahead, remind ourselves of some definitions from the beginning of the calculus course. Suppose you have a function that is continuous. Remember what continuous meant? Simply stated, it's a graph that can be drawn without taking your hand off the page. So this is like a continuous function. So if you have a function, so we say if f is continuous and you limit your attention to a closed interval. So you pick an interval, say from A to B. So if f is continuous and we consider a closed interval, if you remember what was a closed interval, inclusive of the endpoints, then the function over this closed interval has a point that stands tallest, that is, it has an absolute maximum, and it has a point that stands lowest, and that's going to be the absolute minimum. So in this simple picture that I drew, here we have absolute maximum here. It happens to be right at the end point. Here's the absolute minimum. So here's the absolute max, and here is the absolute min. Let's go draw another picture, perhaps with more features in it. Suppose my interval starts at this point, and perhaps I have chosen this point to be my end point of the interval. So here's my A and B. So I've chosen a function that is continuous. If f is continuous, our claim, the claim of this theorem, is that there is a point on this picture, this section of it, that is limited between A and B. Let me go ahead and perhaps darken that. So there is a point of this where we are standing the tallest, obviously here. So here's our absolute maximum. And there's a point that is the lowest. It so happens, it looks like in this picture, our lowest point again is happening at this corner. This is our absolute minimum. If this dip had come way down, then I would have an absolute minimum at that location. So the claim of the extreme value theorem is that if f is continuous and we are looking at it on a closed interval, then there is a point let's call it point C in AB such that f of C is larger than or equal to f of x for any x in AB. Let's see if you understand this peculiar language. We are saying in any of these problems, so long as f is continuous and the interval is a closed interval, there is always some point C. We don't know, we don't prescribe where, but somewhere in this interval, such as this point. There is a point C where f of C beats f at any other point. If I choose another x, say I choose an x here, I'm assured that f at C beats f at x, mean this is taller than that. If I chose an x here, again this is taller than that. If I choose the x here, is taller than that. It's okay for them to be equal, but the property of this is that it stands taller. Then there is a point C in AB such that f of C is larger than or equal to f of x for any x in A to B. Similarly, there is also there is another point or another value D, again in the interval from A to B. That's how we write it, inside interval from A to B. That's a notation they use to say something is inside an interval such that f of D now is going to be shorter than f of x anywhere else. So for example, our D, the lowest point, is going to be accidentally at this corner. That's where it's going to be. So that is pretty intuitive, requires a proof. The proof is not going to be offered in this course, that's part of an advanced calculus class, but we're just going to accept the theorem right now and make use of it. Now we are going to make a very huge important observation, which is, okay, there is these important points we are claiming they do exist. How do you find it? In general, finding such points is not such an easy task unless you know some important things about the function. And that is the subject of the next idea we are going to talk about. That's called Fermat's theorem. Fermat is a very famous mathematician, a French mathematician. Well, mathematics was his hobby, but he was very productive and has influenced mathematics in many areas. Fermat's theorem says the following: if you know that the function is not only continuous but also differentiable, then you can begin to try to find point of absolute maximum or absolute minimum. Here's Fermat's observation. If it says if the following two conditions hold. One is that the function has either a local maximum or local minimum at some point C, and f is differentiable at that point. I don't know how much you remember about this. Here, let's just say that f prime of C exists. Sometimes instead of saying f prime of C exists, I say f is differentiable at C. So the function has a derivative. Then we conclude a very important property. Then that derivative has to be 0. Let's see if you understand this theorem and if you understand the subtleties of this extreme value theorem. What is this theorem saying? Saying if at some point a function wants to turn around, then at the point that it's turning around, its derivative has to be 0. Let's go draw a function. Here, suppose here's a function is going up. Suppose I want to reach a maximum point around here and want to turn down. So when I reach a maximum point, I turn down. Fermat says at the point that you turn down, is at this point C, the derivative has to be 0. Do you remember what it means for the derivative to be 0? Derivative to be 0 means tangent line is what? What's the property of a tangent line when the derivative is 0? When the derivative is 0, tangent line is horizontal. So you have a horizontal tangent line. Well, the question is, why do you expect to have a horizontal tangent line? Why shouldn't the tangent line be some other way? Why can't it be going up or going down or something? We really need a full statement of a theorem to be totally convinced, but right now I'm just going to give you some feeling for the theorem as opposed to a proof of a theorem. Let's go draw this thing again. Suppose you wanted to see if it is possible for the tangent line not to be horizontal. Not to be horizontal means what? Well, it has to either go up or go down, in which case f prime of C wouldn't be 0. Is it possible for me to go someplace and turn around without the derivative becoming 0? Well, if the tangent line isn't 0, say the tangent line is positive and I'm supposed to go up. If the tangent line at this point is positive, then I'll be going still up. I wouldn't be turning down. So I would create a contradiction if you try to turn while the derivative is positive. So if the graph as a positive derivative, you have to still keep going up. Maybe later on you turn down, but now the discussion will move over to that point. Excuse me. Same argument could be offered to say that at the point of turning, tangent line can't be pointing downward. Now somebody might become smart here and say, look, here I can draw a function that turns around and its tangent line isn't horizontal. Here's a function. Here I go up, and now I turn down. Well, doesn't this function have a maximum here? Obviously it does. This is a maximum point. Here's a maximum point. What does this theorem say about this picture? Does this thing have a horizontal tangent line? Well, really, this thing doesn't even have a tangent line. This is a sharp corner. At this corner, tangent doesn't exist. The derivative doesn't exist. So this theorem doesn't really apply here. It says there are two conditions. F is turning around, either has a local max or local min, and the derivative exists. If a derivative exists, it means you're excluding such pictures. Can't have a sharp corner here. If the derivative exists, then the derivative has to be 0. So notice once again, in this situation, we do have a maximum point, and at that point the derivative doesn't exist. So this statement doesn't apply here. Most often, most of the problems that you encounter in this course, the functions have derivatives, and the pictures that you are going to encounter is going to be these type of functions. Rarely you're going to see functions that behave like this. These kind of things do happen in physics and engineering, but we are not going to have much to say about that situation. Okay, so we saw the importance of Fermat's theorem. Fermat's theorem, then it says if you try to find this type of point, go set the derivative equal to 0 and take the problem from there. You still have to work it out and see what else you can get. Now let's make sure we do not misunderstand Fermat's theorem. It's very common to misunderstand the statement of this theorem. Let's go ahead and take a look at another rather puzzling thing. Does the Fermat's theorem say that whenever the derivative is 0, you have either a maximum or a minimum? Is it true? Is it true that whenever the derivative is 0, the function has either max or min? Well, the answer is a resounding no. So one of our headaches is this. Can you go and draw a picture where the function ends up having a 0 derivative that is a horizontal tangent line without having a maximum or minimum? That means without turning around. Well, it's actually quite easy to draw a picture. Maybe you can stop this thing and try to draw the picture by yourself. Here's an example. Suppose I go up and become flat here, so the tangent will be horizontal. Now instead of turning back down, I just flip over and go up. So at this point, around this point, tangent line is horizontal. So we have a horizontal you have a horizontal tangent. But obviously the function doesn't have any maximum or minimum here. There is no turning happening at this location. So we have to be careful not to misunderstand Fermat's theorem. Fermat's theorem doesn't say every case where the tangent line is horizontal you are turning around. It's saying the other way. It's saying that if you are turning around, and you are turning around smoothly, not like in this sharp corner, if you are turning around smoothly, at the point of turning, the tangent line has to be horizontal. That's the statement of a Fermat's theorem. So we talked a lot of rather philosophical sounding things here, but it's important and we need to understand this. This definition of maximum, minimum, and Fermat's theorem give rise to another definition. We have a definition of critical points. Critical points refer to all these pictures that we just talked about. Either tangent line is horizontal when you are either turning around or not turning around. So either your picture is something like this, or perhaps something like this, the derivative is 0, or perhaps you're at a point where the derivative doesn't exist. All of these cases we are going to lump them together and call them critical points. So we say C is a critical point when either the derivative becomes 0. Okay, if the derivative becomes 0, like it became 0 here, or it became 0 here, that's one type of a critical point. Or that the derivative doesn't exist, perhaps like this, or perhaps here's, let me continue this picture. Suppose I arrive at this location and I break the function again. This point also is a critical point. Here the derivative doesn't exist because I have a sharp corner here. The tangent line on the left is something, on the right is something else. This is also a critical point. Any point at which the function ceases to have a derivative is another possibility for a critical point. So either f prime is 0, or f prime of C does not exist all such points are going to be lumped together and we call them critical points. The idea of critical point is going to give us a strategy for finding the maximum or minimum point. Maybe I've been talking too much up on air and not solving any problems or anything. You might feel a little bit uncomfortable with that situation. Let's go ahead and pick up a problem. Let's see if we can do this problem. In the context of a problem, I'll be introducing you to something that the text calls the closed interval method. Essentially telling you how to find the maximum minimum point of a function on a closed interval. Let's just pick a very simple example. Suppose I have a function f of x let's make it very simple here. Say 3x squared minus 12x plus 5. Question: find absolute max and min of f of x over interval from 0 to 3. We proceed like this. See, at the point that the function that has its max or min, either these things are happening at the endpoint or they are happening somewhere inside. At that point in the inside, if the function is differentiable, then its derivative will be 0. Or perhaps function isn't differentiable. So if we come here, we look at this, we say, well, let's see, what is f prime of x? First item is to go ahead and figure out f prime of x. F prime of x, it exists at all x's. There is no point at which such a complication is going to happen. There is no point at which the graph of this is going to have a sharp corner. Everywhere is very smooth. So here's a derivative. Since this is ruled out, we go after this possibility. Is there any point in our interval where the derivative is equal to 0? So let me go ahead, force this thing to be 0. Ask, is there any x at which this is going to happen? Well, that's going to give me an equation. I go ahead and solve that equation in which way I know. This is a very simple equation. 6x is equal to 12. Divide by 6 and you get x equal to 2. We notice that 2 is inside this interval. If it was outside, well, the problem isn't asking us anything about outside of here. It is telling us limit your attention to the numbers from 0 to 3. This happens to be inside that, so we are in business. This is a candidate for being a maximum or a minimum. It could be that it is neither of them, but we have to go and check. How do we check? We make a simple table. Here's x, here's f of x. At the beginning, the interval starts at 0. It goes as far as 3. In between, we are interested at this point 2. So we list the endpoints and we list all the points at which either the derivative is 0 or it doesn't exist. Here we just had one point to consider. Now we take each of these numbers we obtain and plug it in a function we have. So here's a function that is giving us the y values. We take 0 and plug it here and we get the answer 5. We take 2, plug it here, 3 times 4 is 12, minus 12, and they cancel out. And then again I'm getting by accident the same number 5. If I take 3 plug it here, this becomes 27 minus 24. Excuse me, let's write it down. This is 3 times 3 squared minus 12 times 3 plus 5. So at 3 this becomes 27 minus 36 plus 5. That makes minus 4, I believe. So we have this picture that at 0 the function is 5, at 2 it is 5, and at 3 it is minus 4. If you want to find the absolute minimum, you go on figure out the smallest of all these numbers. Smallest of these numbers, of course, minus 4. Absolute minimum value is minus 4, and it occurs at this endpoint of the interval, at the point 3. So here I write absolute minimum point is at 3 and minus 4. This is the x value, this is the y value. This is called the absolute minimum value. This is the point at which it is happening. How about absolute maximum? It so happens that these guys tie. So at some corner and some intermediate point, these maximum happen. So I have at the point 0 and 5, as well as 2 and 5. Excuse me, it looks like I made a mistake here. Let me correct myself. I need a big eraser now. Here's my mistake. This wasn't 5, is that right? So back to the drawing board. At 2, this is 12 minus 24, so that makes minus 12, plus 5, that has to be minus 7. So I better go ahead and correct. So let's go back to square one and see what happened. We took this function, I set the derivative equal to 0, found the root of that, considered the two endpoints and the root that I have found. Make a table consisting of all of these numbers. I evaluate my function at all of these. So I find the y value at all the points I've found. Endpoints as well as the critical points. At 0, no problem, we have 5 here. At 2, I made my mistake there. This was 12 minus 24, it's minus 12, plus 5 is minus 7. At 3, we had 27 minus 36 plus 5, and then that makes a minus 4. Of all of these numbers, the lowest that it gets to be is at this point, at minus 7. Absolute minimum occurs at 3 and minus 7. Absolute maximum happens at this corner at 0 and 5. All of this could have been handled easier if we had the picture drawn first. Since the function is very easy, we can go ahead and draw that that function, but that's not always an easy thing to do. This is a parabola, and we are looking at it between 0, say 0, 1, 2, and 3. At 2, the function is at, say, minus 7. Suppose this is minus 5 and minus 10 and minus 7, say, is here. This is the point with the coordinates 2 and minus 7. At 0, the function happens to be at 5. So somehow it makes it here, turns around, goes up. we are looking at this function just between 0 and so this is the left wall, and 3, that is the right wall. We're just looking between these two, nowhere else. So in this range of numbers, the lowest this function goes is at this point, at the point 2, and here's another mistake, sorry. And -7. 2 minus 7 is the lowest point, and in this range of numbers the highest is at 0 and 5. This is a point with coordinate 0, 5. In that range of numbers, this is going to be labeled as absolute maximum, and this is going to be labeled as the absolute minimum. So this strategy for finding maximum or absolute maximum or minimum of a function is referred to as the closed interval method. Now I guess I better go ahead and do another one of these problems that is a bit more substantial, and also in case I ended up confusing you with my errors, I'll correct that. Let's go ahead. Here's a problem. Find absolute max and min of, say, f of x is equal to x over x squared plus 1 over interval from 0 to 2. So what do we do? Step 1, find f prime. So what is f prime? We have to apply the quotient rule here, is that right? Let me indicate what we are supposed to do. Take a derivative of the numerator times denominator minus numerator as it is times the derivative of the denominator, the whole thing divided by the denominator squared. So what is f prime? Derivative of x is just 1. Remember, we are differentiating with respect to x. We are back to our normal differentiation. Derivative of x is just 1. This becomes x squared plus 1. This is derivative of this one, just 2x times that makes 2x squared divided by denominator x squared plus 1 squared. And that is 1 minus x squared over x squared plus 1 squared. Problems with fractions, we have to be a bit more careful because of the following. What are we after? We are after points where f prime is either 0 or it does not exist. We are after finding critical points. We want to find critical points. where either f prime is 0 or f prime does not exist. Either of them makes it critical. So f prime equal to 0. How would I set a fraction equal to 0? A fraction is equal to 0, so if you have a fraction, let me write on the side, this is an important issue that keeps coming up. If you have a numerator divided by denominator and you want the fraction to be 0, what you exactly want is for the numerator to be 0 and denominator not to be 0. When you say fraction equal to 0, that's what you expect. Well, if I set this fraction equal to 0, what do I get? Numerator equal to 0, 1 minus x squared equal to 0. Denominator, luckily, never gets to be 0 anyway. So we are guaranteed that this doesn't happen, because x squared is positive, you're adding something to it, becomes even larger, and then you just don't get a chance of being 0. So this is the only option, 1 minus x squared equal to 0. That tells you that it happens when either x is 1 or minus 1. Critical points of this function in this category are just these 2 points. In this other category, any point at which f prime doesn't exist, when would it be that a fraction doesn't exist? A fraction doesn't exist, either numerator fails to exist or denominator fails to exist. Those are rather uncommon. The typical way a fraction fails to exist is for denominator to become 0. Back to the same issue. Does this denominator ever become 0? No. This denominator never becomes 0. You start at positive 1, you're adding something to it, so it's not going to become 0. So this situation does not happen. Okay, we don't have any candidate of this style. This does not happen. All that we got, so we're kind of saved. The only points we need to pay attention to are either x equal to 1 or minus 1. Now, out of these two, perhaps some of them are not relevant to our discussion. Or what makes something to be relevant or irrelevant? The problem from beginning says focus your attention to the interval from 0 to 2. For whatever reason, that's our focus. Of these 2 numbers that I found, the only one that falls inside of that interval is x equal to 1. So I go pick that up. This is the only critical point in the given interval. This is the only critical point in the given interval. Okay, now that we have that, we go ahead and make our table. Here's our table. Our table, I have x and then I have y. On the x, I put beginning and end of the interval from 0 to 2, and whatever critical points are found in between them, I list it here. Well, what's the y value? Who was the y? Y is the function to begin with. That is our function f of x equal to x over x squared plus 1. This is the y. Let's write it down here. Y is equal to x over 1 plus x squared. Well, if I put 0 in this, what do I get? If I put 0 in it, I get 0. If I put 1 in it, 1 over 1 plus 1, that gives me 1/2. If I put 2 in it, I get 2 divided 1 plus 4, that makes 2/5. So these are gonna decide for us where is the absolute max and absolute min. How do we decide? Very easy. You just look at these and compare. Who is the biggest of all of them? This is 0.5, this is 0.4. So the biggest is here. So that one gets to be labeled as absolute max. of these values, who is the smallest? 0 is the smallest of these three numbers. So this one is going to be labeled as absolute mean. This is the x at which it happens, and this is the value of absolute minimum. This is the x at which absolute max happens, and this is the value of the absolute max. So we have finalized and given the answer. So absolute max, here are the coordinates of the absolute max. Absolute min, here are the coordinates of the absolute min. Now if we had the graph in front of our face, all of this thing could have been decided right away. But then of course you have to have the graph in front of you. Somebody else has to do that job, and then you can get your information right out of that. So say this is 0, say this is 1, and this is 2, and so on. If you spend a little bit of time to graph this function, you see that this function, the rational function, that looks kind of like this. So what was the interval of interest? The interval of interest in our problem started at here. Use another color. To here. So from here to here was interval of interest. All of these problems come with this window that you're looking through. Look at the function through just that window. So what do we see here? Obviously we see this as absolute max. This happens to be at 1/2. At 1 and 1/2, the function reaches the highest point in this window. In this stretch, the lowest point happens to be here. So we have our lowest point, that would be absolute min, the point 0, 0. So that takes care of that problem. Now some of the problems here offer you more challenge, and most of that comes from complicated functions where differentiation gives you rather unexpected results. Or you might have some problems with respect to domains, or finding critical points and such things. Here, let's take a look at the following problem. It says f of t is equal to cube root of t times 8 minus t. The interval is from 0 to 8. Use a stronger color. What is the issue? The issue is find the maximum and minimum. Find absolute max and min over that interval. Well, what is the problem here? Well, problem is the function is rather unusual. When you differentiate it, you are going to get into a little bit of a hot water there, and then you have to find your way out of that situation. That's all there is to it. Other than that, the idea is the same as before. Now how do you differentiate this? You have two styles to do. Either you apply the product rule, or maybe you multiply first and then you differentiate later. Either way will give you the correct answer. Let me adopt the second style. Instead of writing it this way, it pays to write in exponent notation. Multiply 8 times t to power of 1/3 minus t power 1 times power 1/3. 1 plus 1/3 makes 4/3. Is that right? I want to differentiate this. That's not a big deal. Differentiate this becomes 8 times 1/3. Now what's the new exponent of t? You have to lower this by 1. Here's the problem. It's going to become negative, minus 2/3. Differentiate the other one. It's going to be minus 4/3 t. You have to lower this by 1, so that's going to give you 1/3. Okay, that wasn't all that painful when you took the derivative. So where is the difficulty? The difficulty isn't in differentiation. The difficulty is finding critical points. That is, I have to find where the function doesn't have derivative or where the derivative becomes 0. So our objective is find critical points. Again, what were critical points? One of two things. Either the derivative becomes 0, which means I have to set this thing equal to 0 and struggle with that, or figure out where is it that the derivative does not exist. Well, this is easier to answer here right now. Is there a point at which the derivative doesn't exist? Think about it for a moment before I give the answer. Think for yourself. Is there any value of t at which we cannot calculate this? Well, the clue comes from this negative exponent. Do you know what the answer is now? Negative exponent means that you had the item in a denominator. Is that right? Now, do you know the answer any better? Is there any value of t that's going to be problematic? Yes, you're right. If t happened to be 0, you'll be dividing by 0 and you'll create infinity. So there is a point where the function derivative doesn't exist. That is at the point t equal to 0. Okay, that wasn't all that bad. Now to the bigger challenge. How do I set all of this or all of that equal to 0 and solve it? You can use either this format or this format and work it out from there. Maybe I go ahead and use this format here. So I write f prime of t. I have to take a common denominator. Well, common denominator is a copy of this, so this portion it just transfers through, is 8 minus. If I want to make a common denominator, I have to multiply numerator and denominator of this thing by what? Here, let me indicate it. If you want to make this denominator same as that, you have to multiply it by t to the power of 2/3. Is that right? But if you are doing it to the denominator, you have to do it to numerator too. No, the denominators are the same. So if that's what you have done, let's go ahead and clean up the numerator. 4. Now what's the net exponent of t? 1/3 and 2/3 add up to 3/3, which is just 1. Well, So the whole thing boiled down to this nice expression, 8 minus 4t. What do I want? I want the derivative become 0, that this fraction to become 0. When does a fraction become 0? When its numerator is 0 and hopefully the denominator isn't 0. So I go ahead, set the numerator equal to 0, for 8 minus 4t equal to 0. If I go ahead and solve this, obviously the answer becomes t equals to 2. So we are all done. I found my critical point. So when f prime is equal to 0, that tells me t has to be 2. If f prime doesn't exist, it tells me t is going to be 0. Nicely enough, this point at which the derivative doesn't exist matches one of the boundaries. We go ahead and make our table. Our table excuse me, my pen is running out of ink, I guess. Here's x. Excuse me, we had the t, not x. And our function f of t was t to the power of 1/3 times 8 minus t. Our region started at 0, went as far as 8. In between there are these critical points 2 and 0. At 0, well, it's the same copy as this, we don't need to write it again. The other point is 2. All I need to do is to plug these things in my equation. At 0, when I plug 0 to the power of 1/3, well, that is 0. 8 minus 0 is just 8. 8 times 0 becomes just 0. 2 to the power of 1/3. 8 minus 2, that's going to be 6. How about 8? If I plug 8 in this parenthesis is going to become 0. 8 to the power of 1/3 is 2, but 2 times 0 just becomes 0. So we are all done. Where is the absolute maximum of this whole picture? The absolute maximum is here. How did we arrive at that? Compare these three. Who is the biggest? Obviously it's positive, so it's the biggest. Absolute maximum happens at the point where x is 2 and the y is 6 times cube root of 2. That's the same as that. Absolute min, either of these two could be considered as absolute min. That's fine. We might have several answers. Absolute min, at the beginning it happens 0 0, that is this one, and here's the other one, 8 0. So the procedure we are following here is called the closed interval method. We use that for solving this kind of maximization problem. Okay, I guess that's enough for today. Good luck and God bless.